Okay, so let me paint you a picture. It's April 22nd, 2026. Google Cloud Next is happening in Las Vegas, and Sundar Pichai walks on stage and casually drops what might be the most consequential chip announcement of this decade. Not one TPU, two. And honestly, I was not ready for this. Google just unveiled the TPU-AT and the TPU-8i, its 8th generation of custom tensor processing units. And here is the thing that caught everyone off guard. This is the first time in the entire 10-year history of Google's TPU program that they have split the design into two separate purpose-built chips, one for training and one for inference. This is not just a hardware update. This is a fundamental strategic shift in how Google thinks about AI infrastructure going forward. I've been following the AI chip space pretty closely for a while now, and I think this announcement does not get enough credit yet. So let me break it down for you. Now, before we get into the 8th gen details, it's worth understanding what came right before it. Google's 7th generation TPU, codenamed Ironwood, only hit general availability in November 2025. That chip was already a beast. Each Ironwood chip packed 192 gigabytes of HBM3E memory with a bandwidth of 7.37 terabytes per second. It delivered 4,614 FP8 teraflops per chip and could scale up to 9,216 chips in a single pod, delivering 42.5 FP8 exaflops of total compute. That is more raw compute than the world's largest supercomputer at the time. And here is a number that blew my mind. Ironwood was already 10 times more powerful than the TPU V5P from just one generation prior. That kind of generational leap is insane. Anthropic actually committed to accessing up to 1 million Ironwood TPUs to train and serve Claude models, which should tell you something about how seriously major AI labs are taking this hardware. But Google did not stop there. They were already building the next thing. So here's why splitting the chip design actually matters. Training a massive AI model and running it in production are two completely different problems. Training is about raw, sustained throughput. You need to crunch through enormous amounts of data, run backpropagation, update billions of parameters. Inference, on the other hand, especially with modern AI agents, is about speed and latency. When an AI agent needs to respond to a user or coordinate with another agent in a chain, every millisecond matters. You cannot bottleneck that with a chip that was optimized for a completely different workload. Google actually said that they had been working on these two chips for about 2 years before AI agents were even widely understood outside of research circles. They had internal conversations with DeepMind about where bottlenecks were going to show up in the future, and they designed around those future problems now. I find that really impressive. That is not reactive engineering, that's proactive architecture. So let's talk about what each chip actually does, starting with the TPU-8T, the training monster. The TPU-8T is built for one thing: crushing model training at a scale that makes your head spin. A single superpod of TPU-8T chips connects 9,600 chips together and delivers 121 FP4 exaflops of compute. It carries 2 petabytes of shared high bandwidth memory. Google claims it delivers 2.7 times better performance per dollar over the previous generation Ironwood for large-scale training workloads. That is not a marginal improvement. It's a full generational leap in economics. Each chip has 19.2 terabits per second of bidirectional scale-up bandwidth, and it uses a new network architecture called Virgo Network, which supports a 4 times increase in data center bandwidth and links up to 134,000 TPU-AT chips in a single non-blocking data center fabric with 47 petabits per second of bisection bandwidth. And if you really need to go bigger with jacks and pathways, Google says you can now coordinate over 1 million TPU chips in a single training cluster across multiple sites. The AT also got some serious storage upgrades. They introduced TPUDirect RDMA and TPUDirect storage, which bypasses the host CPU entirely and pulls data directly from storage, effectively doubling bandwidth for massive data transfers. That matters a lot when you're pre-training models at the scale of Gemini. The goal, according to Google, is to cut frontier model training from months down to weeks, and if that's even half true, the pace of model development is about to get noticeably faster. Now, it's time for the TPU-8i, which is the inference specialist. And this is the chip that I personally find more interesting from a product standpoint. The TPU-8i was designed from scratch specifically for agentic AI era. Think about what AI agents actually need. They run multi-step reasoning chains. They coordinate with other agents. They handle long context windows. They are doing autoregressive decoding constantly, which means every single token generated requires a round trip through the model. If your chip's network topology was designed for training throughput rather than inference latency, you're leaving a lot of performance on the table. Google figured this out and completely re-architectured the 8i. It has 3 times more on-chip SRAM than the previous generation, sitting at 384 megabytes per chip. Now that matters because it means that a larger chunk of the KV cache, the memory structure that holds context during generation, can live entirely on the chip rather than getting shuffled in and out of external memory. That directly translates to faster, more consistent token generation. There's also a brand new piece of hardware inside the Collective's Acceleration Engine, or CAE. This is a fixed function block that specifically accelerates the reduction and synchronization operations that happen constantly during autoregressive decoding and chain of thought processing. Google says it cuts on-chip collective latency by up to 5 times. 5 times! That's the kind of gain that completely changes the economics of running AI agents at scale. And then there's Boardfly, a completely new network topology replacing the 3D torus that has been in Google's TPU pod since generation 2. The 3D torus is great for training thought, but for inference latency, however, it's not ideal because it was optimized for sustained bandwidth rather than minimizing the distance between nodes. Boardfly rethinks that entirely and focuses on reducing network diameter, which is the longest efficient path between 2 chips in the fabric. The result is up to 50% lower latency compared to Ironwood, and a single 8i pod can scale up to 1,152 chips and delivers 11.6 exaflops of FP8 compute with 331.8 terabytes of HBM capacity across the full pod. The price performance improvement for inference is claimed to be 80% better than Ironwood. For companies running large MOE models at low latency targets, this is an enormous cost reduction. Now, let me be honest about something. If you look at raw per-chip performance numbers, NVIDIA's latest hardware still wins on paper. The TPU-AT delivers 12.6 FP4 petaflops per chip. NVIDIA's Vera Rubin R200 is rated at 35 FP4 petaflops for training. AMD's MI455X hits 40 FP petaflops. That is roughly a 3-to-1 gap in raw compute per socket, and I'm not going to pretend that's nothing. It's a big deal, but here's the thing, that framing misses the entire point of what Google is doing. Google does not sell you one chip, it sells you a system, and at the system level, the economics flip drastically. A single TPU-AT superpod delivers 121 exaflops. NVIDIA's NVLink connects to up to 576 accelerators in a single domain. Google just linked 9,600 chips in a pod and claims paths to over 1 million chips in a coordinated cluster. The total cost of ownership for a full Ironwood pod configuration has already been estimated at around 44% lower than a comparable GB200 server setup, according to analysis from SemiAnalysis. That gap is likely gonna get even more favorable with the 8th generation. And Google is not just competing with NVIDIA on cloud customers, it's building its own internal AI infrastructure and training its own frontier models on these chips. Gemini, Veo, Imagen, and now apparently Anthropic's Claude models all run on Google TPUs. This is vertical integration done right, and it gives Google a structural cost advantage that compounds over time. Now, here's my honest take on all of this. Google has spent over a decade quietly building something that most people outside the industry did not take seriously enough. The original TPUs were introduced in 2016, and for years the narrative was that NVIDIA's GPU ecosystem was just too dominant to displace. The software moat, the CUDA ecosystem, the developer tooling, all of it pointed to NVIDIA as the permanent winner. But what Google has been doing is not trying to win by having the fastest single chip. It's winning by controlling the entire vertical stack, from the silicon to the networking to the software frameworks to the models themselves. And now, with over 4 million TPU shipments projected in 2026 alone, and a path to 35 million by 2028, the scale of this operation is becoming impossible to ignore. The fact that both TPU-AT and 8i now run natively on Google's own Axion ARM-based CPUs means that the entire host-to-accelerator system is co-designed from the ground up. As Google's own SVP Amin Vahdat put it, when you own the full stack, you can optimize system-level emergency efficiency in ways that simply cannot happen when the host and the chip are designed independently. Both chips deliver up to 2 times better performance per watt compared to Ironwood. Both chips are coming to Google Cloud later in 2026, and both chips represent something I genuinely think is exciting: a future where AI compute landscape is not a monoculture. Competition is good. That's definitive. It's good for pricing, it's good for innovation, and it's good for anyone building any real AI products. The fact that Google is here building chips that are genuinely competitive at the system level makes the whole ecosystem better, and for a company that basically invented the transformer architecture, you would hope that they know what hardware that architecture actually needs. I'm looking forward to seeing the real-world benchmarks when these chips ship, because on paper, this is a very, very serious move.